Hey everybody, welcome to another Khan support video. This one's on experimental probability. So remember, experimental probability just means predicting future outcomes or future likelihoods based off of previous experiments or collected data. So what happened in the past, and using that information, let's make a prediction about the future. So it's not looking at a model and doing a theoretical probability where you analyze a model. You're more just thinking about, all right, what occurred and what does that tell us about what will happen? So let's go through and do it. All right, so let's do number one here. It's a text box. Let's get out of the text box. All right, here we go. Number one. Okay, cool. So it says Tomer owns a daycare center called Kids Care. One afternoon, he collected the age of each person in Kids Care. The following histogram summarizes the data he collected. So here we got the number of people, and here on the bottom we got the age in years. So that basically means that people from 0 to 5 years old, there's 3 of them. From 5 to 10 years old, there's 2, and so on and so forth. It says, based on his data, what is a reasonable estimate of the probability that the next person to enter Kids Care is between 10 and 15 years old? So basically they're saying, all right, what's the likelihood they're going to be in this bin, right, this interval, 10 to 15? So all you're going to do is you're going to say, all right, well, let's look at what already occurred and use that to predict the future. So you're still going to do the same idea of favorable outcomes over possible outcomes. But in this case, you've got a sample space that's given to us as this data piece that they've collected. So here's our sample space, that's the histogram. And it's basically going to be the ages of these people at Kids Care, right? And that's the ages of the kids at Kids Care. So let's write Kids Care. Okay, and let's find out how old these people are. So from 0 to 5 years old, you have how many? 3. And people from 5 to 10 years old, you've got 5 to 10, it's going to be 2. And then from 10 to 15 years old at Kids Care, you have how many of them? 10 to 15, it's 3. And from 15 to 20 years at Kids Care, you've got 15 to 20 years, you've got 1. And from 20 to 25 years, you've got just this 1 as well. So these are all the people that are at Kids Care currently that we've collected data on. So this would be the total of how many total people. 3 plus 2 is 5, plus 3 is going to be 8, plus 2 more is 10. So there are 10 people at Kids Care currently. And they're asking you, based on this information, what's the likelihood that the next person who comes to Kids Care is going to be between 10 and 15 years old? So probability of 10 to 15. What is that going to be? And we have no model to look at, right, except for this data. So we're going to look at this data that already happened and use that. So our favorable outcomes are going to be the number of kids that are right here, 10 to 15. So we can see there's 3. So that's our favorable 3. And that's what this is, right? 10 out of the possible, which is going to be the 10. So the experimental probability says there's a 3 in 10 chance that the next person who joins up to Kids Care will be between the ages of 10 and 15. So that's what you put. You just put 3/10. So you select 3/10 and hit check. That's it. Next question. So it says here, let's scroll this down to the next one. All right, next question. Number 2. It says, Stephen read 12 books, 20 magazines, and 17 newspaper articles last year. So the sample space in this case is Stephen's reading habits, okay? So the sample space is the collection of all possible outcomes. And in this case, it's Stephen's reading habits, right? Stephen's reading list. All right, there's no model for this. We just have past experience, right? What has Stephen read? That's what he chose to read this last year, okay? And what did he read this last year? Well, this last year he read 12 books and 20 magazines and 17 newspaper articles. All right, this is the collection of all the stuff that Stephen read. So what is the total amount of things that he read? 12 plus 17 plus 20. Or 32 plus 17, which is going to be 39, plus 10, so 49. So it looks like there's 49 items that he read, 49 total things that he read in a sample space. All right, it says, based on his data, what is a reasonable estimate of the probability that Stephen's next reading material is going to be a magazine? So they're saying, all right, based on what he read last year, what's the chance that the next thing he reads is going to be a magazine? So that magazine becomes our favorable, right? That's our favorable that we're looking for. And we're going to put that out of the total possible. So magazines is 20, so that's our favorable. And our total possible is 49. So that means that our answer for the probability of getting a magazine or reading a magazine next would be 20 out of the 49. That's it. Now, 20 out of 49 is approximately close to 20 out of 50, right? Which is going to basically come out to 2/5 or 4/10. So it's about 0.4, it looks like. So the closest answer there would be 0.41. Now, I would use a calculator to double check that. So let's do it. 20 divided by 49. That's going to be 0.408, right? So that's going to be the best answer there. It's going to be 41 hundredths. Okay, so that's what you're going to put as your answer. That's it. Next question. It says the following dot plot summarizes the number of vitamins Omar's mom took each day since she started her new diet. Each dot represents one day. Okay, so now we've got a new sample space. It's a bunch of dots that are representing this woman's, I guess, what are they, vitamins that she's been taking, right? So we go over here, we make a new problem here, number 3. Our sample space is going to be the number of vitamins that this lady is taking. Okay, so this is Omar's mom's vitamins, right? Omar's mom's vitamins. All right, and it basically says that each of these dots represents one day. So she took one vitamin twice. She took 3 vitamins once. She took 4 vitamins twice. She took 5 vitamins on one day. She took 6 vitamins on 3 days. She took 7 vitamins on one day. She took 9 vitamins on one day. Okay, cool. It says, based on the data, what is reasonable estimate of the probability that Omar's mom takes exactly 6 vitamins tomorrow? So there's not a lot. I'm not going to copy the values onto this paper. It's not worth it. So we can say the probability that she's going to get 6 vitamins means that that becomes our favorable, right? That's what we're looking for, right? So if we look at the 6, there was 3 of those dots on the 6. 3 days she took 6 vitamins. So there were 3 days where she took 6, right? So we could list it out and say that she did 1 vitamin, right? We can do vitamins and then the days, and we can like list it out, right? 1 vitamin was 2 days, and then 3 vitamins was 1 day, and 4 vitamins was 2 days, and 5 vitamins was 1 day, and 6 vitamins she did that on 3 days, and 7 vitamins she did that on 1 day, and 9 vitamins she did that on 1 day, right? So how many total days? What's the total number of days that we have here? Well, 2 plus 1 is 3, and 3 plus 2 is 5, and 5 plus 1 is 6, and 6 plus 3 is 9, and then plus 2 more, so that's 11, right? So it looks like there's been 11 days so far. Let's double check over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, 11 days so far, right? So the probability that she's going to get 6, okay, on the next thing, based on what's happened previously, means that we're looking at this right here. Well, it happened 3 times previously out of 11, right? So that's our experimental probability, just 3 out of 11. 3 favorable out of the 11 possible. So that's going to be 3/11ths. That's how you do it. It's literally the number of times that 6 vitamins were taken, right? How many days did you do that on, compared to the total number of days that's been collected. And Then you're going to take a calculator and you're going to go 3 divided by 11 on the calculator. 3 divided by 11 is going to be 0.27272727. So this is going to be the same as 0.27 repeating. And they like you to round it off, it looks like, to the nearest percent. So when you think about that, that's going to be 0.2727, right? Which is going to be when the nearest percent, it looks like it's going to be 27.27 repeating percent. And they want to round to the nearest percent. And since that 2 is going to round down, that would be approximately 27%. And that is the answer, 27%. That's how you do it. All right, the next problem, let me add a little page here. Okay, the next problem, we got a new sample space, right? Our new sample space is this table, right? So you've got this number 4 here. And let's just make this number 4. I think it's number 4. Yeah, it is number 4. The table shows the number of feathers Patsy the peacock sold at each of the 8 festivals this year. Okay, so basically you've got this table, right? And you've got 3, and then 6, and then 1, and then 4, and then 2, and then 3, and then 7 and 2. And this is the table that they've given you. Like this, these are the 8 different festivals, and what she's done on all the 8 festivals. Okay, so this is our sample space, right? This is our sample space that we have to work with. Okay, total possible outcomes. Based on this data, what is the reasonable estimate of the probability that Patsy sells fewer than 5 feathers next festival? Well, each of these blocks is one festival, right? So fewer than 5. So we're looking for probability of fewer than 5. Fewer than 5. So it can't be 5, it has to be less than 5, right? So let's look at the ones that are fewer than 5. Let's mark it up with a highlighter, shall we? So looking at this situation here, we've got the 3 is fewer than 5, the 2 is fewer than 5, the 3 is fewer than 5, the 1 is fewer than 5, the 4 is fewer than 5, and the 2 is fewer than 5. So all of those are things that are fewer than 5. So they're what we call the favorable outcomes. So those are all the things that are fewer than 5. So now we can go in here and we can say that the answer is going to be 1, 2, 3, 4, 5, 6 times that occurred out of the total number of festivals, which was 8, right? So 6 out of 8 is the probability we're working with here, which is 3 out of 4, which is 0.75, right? So that's 0.75 or 75% chance. So it's likely that she's going to do something that is less than 5, right? And that's what I would say the answer is. All right, next question. Let's go through the next one here. And that's going to be the following frequency table summarizes the number of children that dads in Dad's Club have. Okay, sounds good. So we're going to take a look at that. Let's first write our sample space out. This is number 5, question 5. And so we have our sample space that we're going to work with. That's the collection of all possible outcomes. In this case, all the data collected. And it says that the number of children and the number of members. Okay, that's interesting. All right, so these are the number of members are the dads, okay? How many of the dads had, and the number of children they have. Okay, perfect. So if we were to like write this out, we would say the number of children and then the number of dads or members, right, that have those children. So I'm just going to write number of dads there. Okay, number of members, they said. I'm going to say dads. Why not? Okay, so what's the relationship here? We know that there are 1 children, there were 6 dads that had 1 children. There were, for 2 children, there were 4 dads that had 2 children. For 3 children, there were 8 dads that had 3 children. That's quite a lot of parents who had 3 children. And then you have, for 4 children, there were only 1 dad who had 4. And for 5 children, there was only 1 dad who had 5. So these are quite large families, really. 3 kids is a big family, and there's 8 dads who had 3 kids. All right, there you go. So this is the data that we've been given, right? It says, based on this data, what is the reasonable estimate of the probability that the next dad to join Dad's Club has fewer than 3 children? fewer than 3 children. So we're looking at probability that a dad has fewer than 3. Fewer than 3 children. So that it becomes our favorable, right? So we're looking for things that are less than 3. So when we look at that, we can say, all right, fewer than 3. It's not going to include 3. It's going to be the things that are less than 3. So that's going to be 1 and 2 kids, right? And that's a total of 10, right? That's 10 that we're looking at there. So that's our favorable 10. And then our possible is going to be all of the dads, right? So how many total dads are there that are members of this dads club, right? And this is the dads club sample space. So there are 6 plus 4 is 10 plus another 10 because 8 plus 1 plus 1 is also 10. So there's 20, right? So that tells you that there's going to be 10 out of 20 or 1/2, right? So that's 0.5 or 50% of the dads previously had less than 3 kids. So it's likely that there's a 50% chance that the next dad who joins has less than 3 kids. So that would be 50%. And then the next one, let's do this one. Let's do this one over here, 6. And it says, all right, we got some data again. So it's another sample space here. We got 3 and 4, and write that out. 4 and 1. And I'm writing out so when you guys look at this, you can see the sample space. Otherwise, you wouldn't have an example of the sample space. 1, 1, 2, 1. So there's our table of values that they've given us. So I can, oh, that's really sloppy. Let me try to write this a little bit nicer and cleaner for you guys. Okay, cool. So here's our sample space, right? The collection of all the things that have occurred before in this case. And it says the following table shows the number of goals that the Texas Sharpshooters scored in each of their 8 hockey games this season. Okay, that's fine. Based on this data, what is a reasonable estimate of the probability that the Texas Sharpshooters score exactly 1 goal next hockey game? So the probability of 1 goal, only 1 goal, right? So this is the number of goals per game, right, basically. So how many times does that occur? Let's mark it up. We want to highlight the one time with it's just 1 goal. Oh, it happened 4 times. 4 out of 8. So there's our favorable. It's going to be 4 out of the 8. And then that's going to be, of course, 1 out of 2, which is, of course, 0.5, which is, of course, 50%. So half the time, they get only 1 goal. And last but not least, we've got another dot plot. So let's do the dot plot. Let's scroll this down and record the dot plot information for our sample space here. So last one, which I'm very excited for because this is taking me a long time to go through and explain this process. Okay, so number of pets, right? For the following dot plot shows how many pets each customer owned before entering Jeremy's pet store today. Each dot represents 1 customer, all right? So you basically have got the number of customers and then their number of pets that they have. And so it's a little table, right? 0 customers. Sorry, 0 pets. Huh? 1 customer has 0 pets. So I don't know why they're at a pet store. Maybe they're buying it for a neighbor or something. Then you've got 1 pet. There was 1 customer, right? 1 pet, 1 customer. 2 pets, there were 2 customers. 2 pets, there were 2 customers. Then 3 pets, there were 3 customers. This is kind of funny. And then 4 pets, there was only 1 customer who had 4 pets. And 5 pets, there were 2 customers who had 5 pets. And 6 pets, there was only 1 customer. Let me move this over. 1 customer that had 6 pets. It's a lot of pets. And then 7 pets, there was only 1 customer who had 7 pets. And 8 pets, there was only 1 customer who had 8 pets. These are people who love animals. So now we think about this, right? We got to find the total number of customers. So how many customers were in the store today? 1 plus 1 is 2, 2 plus 2 is 4, plus 3 is 7, plus 1 is 8, plus 2 is 10. Looks like there were 13 people who entered the store. Let's check it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yeah, there were 13 people entering the store. Now it says based on this data, what is the reasonable estimate of the probability that the next customer to enter the store has exactly 3 pets? So that means that I'm looking for the probability of 3 pets. The probability of 3 pets. Okay, cool. So how many of these people had exactly 3 pets? Let's look at the list. Well, there were 3 that had 3 pets right there. That is our favorable. So that means that we're going to have 3 as our numerator. Okay. The denominator is the total number of people who entered the store that day, which in this case was 13. So we're looking at 3 out of 13. Now they ask us to put it in decimal form. So you're going to do a calculator and you're going to say 3 divided by 13. So 3 divided by 13 is 0.2307, blah, 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 blah. So I'm just going to do approximately here 0.2307. And then we can, of course, approximate that to the nearest, let's say, hundredth. So it looks like that would be about 0.23 or 23% of their customers had exactly 3 pets. And so that would be 0.23, right there. And that's how you do it. And that took a long time. Sorry, guys, but I wanted to explain everything to you.